This unit that we're studying is all leading up to talking about exponential functions, in particular, what different types of models exponential functions can exhibit. One type of model that an exponential function exhibits is a growth model, where we see as the x values get bigger, the y values grow exponentially. The other one is called a decay model, that as the x values get bigger, the y values get smaller in an exponential way. We'll see both of those momentarily. In general, an exponential function is defined according to y equals a times b to the x. A and b have very significant importance in this equation. A is called the initial value. It's called the initial value because it's the value that the function takes on when x is equal to 0. Graphically, we usually call that the y-intercept, so long as the function hasn't been transformed. The other value is the exponential base. The b represents the base, and that tells us the particular relationship that the exponent grows by. If we look graphically at some examples, one model of exponential growth is the function f of x equals 2 to the x, in which the b value here is 2. That should tell us something about how exponential growth models grow. I'll go ahead and give you the relationship that if b is bigger than 1, then your graph of the exponential function will show growth, exponential growth. That as x values get bigger, the y values get bigger and bigger as well. That indicates something about the in behavior to us, that the limit as x approaches infinity of the function is equal to infinity for an exponential growth model. For an exponential growth model, as we look at the other direction, what happens is that x values get smaller and smaller. Well, the y values you would think get smaller and smaller, but they don't actually. Well, I guess they do, but they don't decrease infinitely. They decrease in a way so that your y values are approaching 0. You can test that numerically. What that means for our end behavior on the left side is that the limit as x goes to negative infinity of the function is equal to 0. Interesting. We haven't seen a case necessarily where one side of the end behavior is a finite value, whereas the other side is an infinite value. The other model is an exponential decay, that in exponential decay, the graph is shown decreasing if the base is between 0 and 1. In this case, we see that b is equal to 1/2, which is between 0 and 1. Therefore, I know that the graph will show exponential decay. What is shown by the exponential decay? Well, just noting some relationships between growth and decay. In a decay model, it's almost as if it's the growth model but reflected across the y-axis. So, as x gets bigger and bigger, the y values will tend towards 0, or the limit as x goes to infinity of f of x tends towards 0. As long as there's not transformations, I want to make that clear too. And the limit as x goes to negative infinity of the function is positive infinity. In both models, as long as the function is not transformed, you should see that the a value in those cases is 1, and our y-intercept in both of those cases is 1. Interesting. How can I broaden this understanding? Well, let's make some broad statements here that in both cases where there was not an a value, or the a value was 1, the y-intercept was 0, 1. And in both cases, there is a horizontal asymptote at y equals 0, that the graph gets closer and closer and closer towards y equals 0, but it never actually crosses that or touches it. Generally speaking, we'll see that relationship stay as long as the function is not transformed in any way other than the initial value, the a, being transformed. There's some other things that can be said about exponential growth and decay, that in a growth model, I can state the base in terms of the way that it's growing. For instance, if I had a graph f of x is equal to 1.02 to the x, well, b in that case is 1.02. I can rewrite that as 1 plus 0.02, and that should indicate to me, if I were to rewrite this in percentages, the way that the graph or the function is growing, that it starts with the initial 100% and is growing by 2% each iteration, that 2% is called the rate of increase or the rate of growth. As well, I can do a similar thing with decay, where if I had the function f of x is equal to 0.97 to the x, I can rewrite that as b is equal to 0.97, I can see from the graph, which is 1 minus 0.03. Rewriting in terms of percentages, that would be 100% minus 3%. So our rate of decay is by 3% per year. And you can identify that by stating that the growth can be rewritten as 1 plus the rate of decay, and the base can be rewritten in decay models as 1 minus the rate of decay. So let's look at one particular example, a real-world example specifically. The Tesla Cybertruck has a starting price of $39,000. The function y equals 39 times 0.8t can be used to model the value of the car in thousands of dollars, t years after it was purchased. Does the function represent growth or exponential decay? Let's look at what the graph or the equation says without even looking at the graph, times 0.8 to the t. If I look at the base, I see that the base is equal to 0.8, which is between 0 and 1. Therefore, I can conclude with certainty that this graph will show exponential decay. What does that mean? That means that every year after I've purchased that Cybertruck, the value of the truck, the value numerically or cash-wise, is decreasing. That it gets less and less valuable as you move through time, which should make sense. What is the rate of decay? Well, I have two pieces of information. I know that the base is 0.8, and I know that the base can be rewritten, since it's a decay model, as 1 minus the rate of decay. 1 minus the rate of decay. So using those two pieces of information, I can say 0.8 is equal to 1 minus r. Subtract 1 from both sides, and I get negative 0.2 is equal to negative r, or that r is 0.2. If I convert that into percentages, that's 20%, meaning that the rate of decay is 20% per year. In terms of the problem, what does that mean? That means that the value of the Tesla truck is decreasing by 20% per year. What is the value 1 year after purchase? Well, that's not so bad. I just take the equation, y equals 39 times 0.8 to the t, and substitute in t equals 1. 39 times 0.8 to the first power. If I use my handy-dandy calculator to figure out what that should be, 0.8 times 39, I get that it's 31.2, meaning that the Tesla the Tesla truck has a value of $31,200 1 year after purchase. What about 5 years after purchase? Well, it's the same exact thing, that you would substitute in 5 for t to the 5th power. And whatever you simplified would end up being the value of the truck. How many years after purchase is the Cybertruck valued at $0? Well, let's think about this. If we think about it as a decay model, was there any time in which the decay model could ever reach 0? No, because there's a horizontal asymptote at y equals 0, meaning that it never reaches $0. And I know this because it's an exponential decay model. And exponential decay models have horizontal asymptotes. At y equals 0. Therefore, since the graph will never actually reach 0, it'll tend towards 0, but it never will actually reach 0, we can pretty realistically conclude that the Tesla truck will never be valueless. It never will be worth $0. One other way in which you might see some exponential functions or exponential relationships displayed is through a table. In the next video I make, I will go ahead and go through all of these, or maybe several of these examples, but I'll just go through the first one, or the first one, this one, and that one, so you can see, generally speaking, how that works. Consider the table shown below. An exponential relationship exists between the x and y values. Determine whether each shows growth or decay, and find the value of the exponential base and the value of the initial value of a, I guess. A is easy in this first table. A should be whatever the y value is whenever x is 0. So in this first model, a is equal to 600. How do I determine what the exponential base is, though? I think about, as I move from one step to the next, what is happening? What did I multiply the y values by to get from one step to the next? I multiplied by 1/2. And if that's consistent as I move through the rest of the table, which it does happen to be, then that is what I can identify as my exponential base. That tells us something immediately, that we know with certainty that this has to be an exponential decay model because b is between 0 and 1. You can also have some additional evidence that the y values are decreasing, so more than likely it's a decay model, but you have to check that. So our equation should be 600 times 1/2 to the x. That is our specific exponential model shown in this table. And we can state that it's decay. It's an exponential decay. What if things aren't so simple, though? Like this third table. In this third table, I'm not told the y value whenever x is 0, so I'm going to have to use some different method to figure out what the a value is. I'm going to have to do that as well with the b value because I can't easily think, what do I multiply 2 by to get 0.6? So what if I thought about it backwards? How do I figure out what to multiply 2 by to get 0.6? I can think of that as taking the ratio of 0.6 and 2, that 2 times some number is equal to 0.6. Therefore, that number has to be 0.6 divided by 2, or 0.3. I'm going to rewrite that as 3/10. Generally speaking, it's okay if you write it as 0.3 for us continuing forward, but it might make your a value look a little funky. That's okay though. So we're able to easily identify what the b value is from here. Let's see if that stays true. When I multiply 0.6 times 0.3, do I get 0.18? I do. So we still have some information, a times 0.3 to the x, but I need to figure out what the a is. And we've done problems like this before where I don't know what the a value is, so what do? I pick any of these points, substitute in, and solve for a. I'm going to pick the first one just because it's easy. Um, 2 is equal to a times 0.3 to the second power, or 2 is equal to a times 0.09. Therefore, a has to be 2 divided by 0.09, or when I bring out my handy-dandy calculator, 2 divided by 0.0, uh-oh, 009, I get, oh, I wrote that wrong. Sorry. That should be 0.09. So let's try that again. 2 divided by 0.09, and I get 22.2, about. So the exponential model should be a times b to the x, or 22.2 times 0.3 to the x. Since this has a b value that's between 0 and 1, this is an exponential decay model. That's all I'll leave for now. I will work the other examples in a separate video.